Hi everyone, Mrs. Hanson here again, picking up our lessons, this time investigating the third law of thermodynamics. And in this investigation, we will study that the entropy of a pure, perfect crystalline substance assigned 0 Kelvin, which we know to be absolute zero, nothing colder where all molecular motion would stop. And therefore, if there's no molecular motion, entropy is assigned 0. For all perfect crystalline substances. Of course, these are theoretical substances because we've never achieved absolute zero. But what we do is make careful measurements to determine the temperature dependence of a substance's entropy and then simply derive these values under specific conditions. Standard entropies, which are given the symbol with this sub-naught superscript, and we measure those at 298 Kelvin, which we know is standard temperature, 25 Celsius, and at 1 atmosphere of pressure. We called those standard temperature pressure values. And those values are determined for 1 mole of a substance at 1 atmosphere and 298 Kelvin. What we can do then is compare the entropy change from that pure crystalline substance at 0 Kelvin to the 25 Celsius or 298 Kelvin species. And those values are computed and placed into those standardized charts. Again, I recommend looking over those standardized charts. It's in our appendix of our e-text, and you can find those thermodynamic qualities there. Just like we had in our last chapter, calculating the enthalpy of a reaction, of the system, if you will, we took the sum of the enthalpy of reaction of products minus reactants. Do you see how these standard states are used in the same way for entropy here? The enthalpy of reaction from last chapter, products minus reactants, finding the enthalpy change as a reactant's turn to product. We can do the same formula to find the change in entropy of a reaction, and I can put that little RXN here to remind us that's the system or the reaction that we're studying. It's the sum of the entropy of the products minus reactants. And remember that it is coefficient dependent when we calculate those values. So these standard entropies, this little symbol here means at standard conditions, which is the 298 Kelvin and 1 atmosphere pressure. If you happen to have an aqueous solution, it would be 1 molar for standard conditions. And to calculate the standard entropy change as reactants turn to products, we look up each value in our appendix, the standardized thermodynamics chart, and we take the sum of the products minus reactants. Now, to just share with you, when we look at some of these entropy values, pulling them from our appendix or the standardized chart we're provided, notice that every value is positive. I'm just making that note here. And that's a critical observation because, remember, at 0 Kelvin, the third law of thermodynamics would say every pure crystalline substance would have a value for entropy of 0 joules per Kelvin mole. That's its assigned value. And so if that is the entropy, it's not even changing, it's just the entropy of that crystal, you begin to warm that, any value will go up for entropy as it gains kinetic energy through thermal energy and vibrations and so forth. So entropy values always positive. Notice here the graphite, the diamond, and the vapor form of carbon, the elemental form of carbon. Now we know that graphite is a more chaotic system than a diamond, which is more regularly held in fixed positions. And look here, when it goes into the gaseous form, how quickly the entropy value rises. Gases are much more chaotic, many more microstates than in diamond or graphite form. Notice also the trend that as the, look at solid calcium versus gaseous argon, significantly more entropy when the elements are in a gaseous phase. And notice also that the trend shows halogens, fluorine, chlorine, bromine, and iodine. Bromine, of course, is in a liquid phase, so it would have lower entropy. Iodine is in a solid phase, so it has lower entropy. But if I'm comparing the two gaseous halogens, fluorine and chlorine, the heavier molecule will have greater entropy. So just to remind us, as you think about values of entropy, consider their state of matter, solid, liquid, or gas. Gases having the highest entropy, liquids would be somewhat less, and solids, of course, the lowest entropy. But also compare molar masses where in the same phase. So fluorine and chlorine are both gases, and we recognize the pattern that the heavier molar mass would have an increased entropy. So just some examples of standardized values for different compounds that we see. You can notice over here, here's steam versus liquid water. Of course, gaseous water having a much higher entropy than in the liquid phase, even though they're the same substance. So the dominating factor there, of course, is the state of matter. So let's take a look at an example problem where we're being asked to calculate the standard molar entropy for the reaction. So let me read the question for us. It says, consider the reaction of hydrogen and oxygen to form liquid water. So we have the elemental form of hydrogen as a diatomic molecule in the gaseous phase, so H2 little g for gas, is reacting with the elemental form of oxygen in its natural state is O2, assigned a little g for gas. And it's saying we're going to form liquid water. And so its state of matter will be a little L for adjective for liquid. We'll balance this quickly with a 2:1:2 molar ratio. So this is the reaction. We're being asked to calculate the standard molar entropy for the reaction. Now I just took a screenshot and inserted it into this, this diagram here, just to show in the appendix that the first column will always give us the standard heat of formation, that's enthalpy. The second column always gives us Gibbs free energy, which I know is coming in our next lesson. Free energy will be talked about next. And it's the last column that gives us the entropy values. So oftentimes we want to make sure that we remember that it goes delta H, delta G, delta S. And so if you're quickly scanning down a long appendix page and you lose sight of what the top of the column is reading, what we're reading, just remember it will always go in that order. Enthalpy, Gibbs free energy, followed by entropy in the last column. Another observation to make, I want us to notice units. Notice that enthalpy is in a kilojoule per mole. Gibbs free energy is the same, kilojoule per mole. But critically important to note that entropy is in a joule per mole Kelvin. And so when we go back and start placing these variables in the same equation, if this is a kJ per mole, and this guy is a kJ per mole, but this is a joule per Kelvin mole, we have to be sure that we have like units in any type of problem where these variables appear together. Most often you're going to switch your entropy from joules to kilojoules just so we have unit agreement. But a very important thing to note is that joules per Kelvin mole are stamped on the entropy values. Otherwise, the numbers are just so small in our tables. All right, so how do we go about tackling this problem? Consider the reaction of hydrogen and oxygen to form liquid water. What about the entropy? Well, let's make a prediction about the sign, shall we? During the course of this reaction, we have 3 gaseous moles on the left side forming 2 liquid moles over here. Now, I predict in my just thinking about changing of matter from gaseous moles to liquid moles, it's becoming more organized. Plus, we have 3 moles converting into 2 moles, which is also a more organized state. So I'm predicting that when we're done calculating, we better end up with a negative sign on our entropy just to know that we've calculated correctly. The system, as it proceeds from left to right, is becoming more organized. Well, what I've done here now is looked up the values of each of our components here. I found hydrogen, and I screen clipped it and wrote 130.7. So let me just make a note here that this is 130.7 joules per Kelvin mole. I found oxygen, 205.2. And I found both gaseous water and liquid water. Make sure you're checking the correct adjective. Is it a solid, liquid, or gas? And in the liquid phase, 70 is the assigned value for the entropy of liquid water. We know that the delta S for this reaction, or the system, same words, is equal to the sum of the products minus reactants. So the products, of course, would be 2 waters. We have the coefficient of 2 going to be dispersed through the 70, and that's a joule. Let me write the unit there. A joule per Kelvin mole. Here is the products, which represents 2 liquid moles of water, minus, and the sum of the reactants. Now here we have 2 moles of hydrogen, so we have to take 2 times the 130.7 and add that to, and we have 1 gaseous mole of oxygen, and it's assigned 205.2. And there is the sum of the entropy values of the reactants. Now hit that with me on your calculator and see what we find for our delta S of the reaction. So in a parenthesis, let me clear screen, parenthesis 2 times 70, close parenthesis, minus, I'm going to open up a new parenthesis and go 2 times 130.7 plus 205.2, close parenthesis, and I come up with the value of negative 326.6, and the unit again, joule per Kelvin mole, or mole Kelvin, doesn't matter which order you place them. Did our prediction come true? We predicted that it would be a negative sign because it's becoming a more ordered system, and yes, indeed, it did come out negative just as we predicted. So we've employed the 3rd law of thermodynamics to find the sum of the products minus the sum of reactants to find the overall entropy change of our system. And we found products minus reactants is a net value of negative 326.6 joules per Kelvin mole. Let's try one where we're given the standard entropy change of each of the reactants and products from the standard values found in our chart. So I'm reminding you where you're finding these, you have to go look. They're not going to always be stamped on your homework problem. But on your test, let's say this for sure, you'll see this format more like this than a big standardized chart where you have to go find them. On the test, you're going to be provided the data. In other words, you're going to have a snapshot similar to what I've been screen clipping on these practice problems. Now remember, in the standard thermodynamics chart, the heat of formation is always in the first column. Gibbs free energy will be in the second column, and entropy will be in the third column. We want to emphasize kilojoule per mole, always for heat of formation. Gibbs free energy, always in a kJ per mole as well. But this is the difference. Entropy is given in joules per Kelvin mole. We want to make sure that units are always in agreement if we're using these variables within the same algebraic formula. Well, this is a combustion problem of propane, isn't it? A hydrocarbon with 3 carbons is called propane. It's going to combust in the presence of oxygen, releasing carbon dioxide gas and gaseous water. Calculate the standard entropy change for the reaction. The reaction is another way of saying for this system. Alrighty. So we want to just find the sum of the products minus reactants. Now, carbon dioxide in this value is given to me as 213.8. Gaseous water is 188.8. I just like to tabulate underneath each ingredient. We have propane given to us as 270.3. And then elemental oxygen at 205.2. Now, this would be a good pause before we jump in. I want to remind us why we're seeing zeros for the element oxygen. Do you recall when we defined the heat of formation? How much energy does it take to build a compound from the elements it's made of? And we decided that elements, since they're in their natural state, we don't build those. They are the building blocks we have in nature. So 0 was the assignment for any element in its natural state. And you'll also see the same holds true for the Gibbs free energy. Any element in its natural state is assigned 0. But entropy will always be a positive number. 0 entropy was assigned in the third law of thermodynamics as any pure crystalline solid at 0 Kelvin. Remember, these are at 25 degrees Celsius. So as we warm from 0 Kelvin, 298 Celsius, or 298 Kelvin is the, let me write that so it makes sense. 0 Kelvin has 0 for its entropy. Well, here we are at 298 Kelvin, so obviously as it warms up, every substance, I don't care if it's a pure elemental form, every substance will have a positive entropy value. So that's why we're seeing, even though oxygen is in pure elemental form, it has a 0 enthalpy, 0 Gibbs free energy, but it has a positive 205.2 entropy value. Just wanted to make sure we see that distinction. All right, so here's our setup, isn't it? Our setup is going to take, well, I need that reaction. We have 3 moles. I'm going to give myself a little room to work. And let's change color here. We'll go blue. We have 3 moles of carbon dioxide. And carbon dioxide had an assigned value of 213.8 plus 4 gaseous moles of water at 188.8 apiece. So here's the sum of the products minus, down here I'll write out the reactants. We had 1 gaseous mole of propane at 270.3 plus 5 gaseous moles of oxygen at 205.2. Here are the reactants. The sum of the products minus reactants. Let's solve for this and make sure we get a common answer. Please don't cheat yourself out of the practice with your calculator. 3 times 213.8 plus 4 times 188.8. Just to kind of check so far, the sum of the products we're getting is 1396.6 minus, not that I had to write that, I just want to make sure we're at a common answer so far, minus, I'm going to do this in parentheses, minus 270.3 plus 3 times, oh, I'm sorry, that's 5. Let me back that up. 5 times 205.2. I'm going to just read my screen carefully here. We have 270.3 plus 5 times 205.2, and that comes out to be 100.3 joules per Kelvin mole. I just re-hit this to check. Here I got 1296.3. Just doing a quick double check. 1396.6 minus that answer, and we get 100.3. Yep, I got the same answer twice. I like to double check my calculations. Now notice this here is a positive entropy. Let's double check and make sure that makes sense. On the left side, we had 6 gaseous moles. On the right side, we have 7 gaseous moles. A total of 3 and 4 combining to give us 7 gaseous moles. That's more particles. More particles creates more microstates, more chaos, more disorganization. Therefore, that makes sense that our entropy value would come out positive. We're creating more gaseous moles as reactants proceeded to products. So here's an example of that, what I emphasized in the last slide. Thermodynamic properties of heat of formation, Gibbs free energy. When we have an element in its natural state, they are assigned zeros for heat of formation and Gibbs free energy, which I know we'll talk about in our next lesson, but they are standard values for any element in its natural state. Here's another example of solid aluminum. That's an element, how we find it in its natural state. But every compound has a positive entropy value. So notice that even though we have zeros assigned to the elements for enthalpy and Gibbs free energy, they are indeed positive numbers for entropy. Now here's an example old test question. At standard temperature, 298 Kelvin, all of the following substances have a standard free energy of formation of 0, except what? So what this question really is asking you is, which element is not found in nature? Whoops, I wrote element twice. Which element is not found in nature as stated in the directions? So choice 1, gaseous bromine. Choice 2, solid iodine, rhombic sulfur, gaseous chlorine, liquid mercury. Which element stands out to you as being incorrect in its natural state? And I talked about this just a moment ago in this entropy chart. When I had talked about the halogens down here, we noticed that bromine is actually a liquid at standard conditions. Iodine is indeed a solid. Fluorine, chlorine are gaseous. We can also see mercury as a liquid in its natural state. There's only 2 elements in the liquid state, and that's bromine and mercury are the only 2 elements that are liquids at room temperature. And so this right here is not correct, because the element of bromine in its natural state would be a liquid. That would be assigned a 0. And since it's in its gaseous state, it's going to have a positive form. So it would take energy to turn bromine into its gaseous form from its natural state of a liquid. So that's the exception. Every other description of these elements is how we indeed find them in nature. S sub 8 is the rhombic form of sulfur, that pretty yellow flowered powder we see. Okay, good reminder from drawing in concepts from last chapter to this chapter. Let's take another practice using the third law of thermodynamics. We're being asked to calculate the entropy change for the following process, and it may simply say the evaporation of ethanol. You might not be given the actual equation, but we can deduce that what that would mean. To evaporate means to go from a liquid to a gaseous phase. And so ethanol, with its chemical formula, C2H5OH, in the liquid form, using the standard tables of thermodynamics from our appendix, I looked it up for us just to save the time and found its value of 160.7. In the gaseous form, 282.7. So I did that work for us and looking up in the appendix their standard entropy values. Now let's decide if our entropy change, which I know for this process, the entropy change for this reaction, even I wouldn't say it's truly a reaction simply because it's a physical process. So let's just call it of the system. We're going to take the sum of the product minus the sum of the reactant. And since there's just one ingredient, it's a simple subtraction. But I wanted to make a prediction with you about the sign on entropy. Will it come out positive or negative? If a liquid is turning into a gas, gases, of course, are more chaotic system. I predict that this is going to have a positive sign as the phase change from liquid to gas increases molecular entropy. The system becomes more chaotic, more disorganized. And when I subtract 282.7 minus 160.7, I do indeed get a positive value of 122 joules per Kelvin mole. Now I selected this example for a few reasons, really, to remind us that the delta S of the system is the same as if you see it written as the reaction, because the reactions are the system that we're focusing on, and of course the surroundings would be everything else. And also the importance of predicting the sign on your entropy change. Before you even calculate anything, you can predict if the entropy value should come out positive for becoming more disorganized, or should it come out negative as microstates decrease and the system is more organized. Well, let's take a next step in the second law of thermodynamics and kind of integrate that in with the first law of thermodynamics, where we learned in the first law the total amount of energy in the universe is the sum of heat and work. First law of thermodynamics. And we defined system and surroundings in that process as well. We defined the entropy of the system to be related to the heat, which is Q, divided by the Kelvin temperature. And that gets us joules per Kelvin. That's the unit on entropy. If we're focused on the system, the heat is focused on the system. Or we can turn our attentions to focus on the surroundings. The entropy of the surroundings is equal to the heat of the surroundings over the Kelvin temperature. That also gives us the joules per Kelvin unit assigned to entropy. We know that the system in the surroundings is always equal to 0. So therefore, if I just rearrange this equation, the heat of the system is equal to the opposite sign on the surroundings. Q of the system is negative Q on the surroundings. Well, let's rearrange and come up with this particular equation. So this is the one that we will know come test day. I'd like to know how to calculate the entropy of the surroundings. To do so, I can use the heat of reaction of the system divided by the Kelvin temperature. So this is the enthalpy change of the reaction. Now let's be clear. On the last slides, we've been saying the entropy of reaction is equal to the sum of the products minus the sum of the reactants. That's what we were just playing around with. And that this reaction is what we called the system. Sum of the entropy change of reactants minus the sum of the entropy change of products minus reactants. But if I want to know the entropy change of the surroundings, I use the enthalpy change. Notice the negative sign because that's this important part here. The enthalpy change of the heat of reaction over the Kelvin temperature. And so delta H is enthalpy, heat of reaction. And of course, we also remember that the entropy of the universe is simply the sum of the system and surroundings. The system is the reaction. The surroundings is everything else. So if we measure the system, we can indirectly measure the surroundings, knowing that they give us the total amount of entropy change in the universe. All right, I know, right? Let's take a practice problem. Let's consider the following reaction at 298 Kelvin. This is a combination reaction. We have 4 moles of solid aluminum reacting with 3 gaseous moles of oxygen, forming 2 moles of aluminum oxide. Well, I would predict this is a decrease in entropy because we're rearranging gaseous moles and forming fewer moles of solid phase. So right away, I'm predicting the entropy change is going to be negative. The system is becoming more ordered. But let's prove it to ourselves. We're asked to calculate the delta S of the system. Now I want you to remember the delta S of the system is the same thing as saying delta S of reaction, because that's what we're studying is our reaction, and so therefore it's our system. And that means our reaction, I wrote H. This system here was going to be given to us as RXN or system. Those are the same things. And that's going to be taken the sum of the entropy of products minus reactants. So let's go to work and solve for that. Here we have aluminum oxide as our product. Remember, it's the very last column. That's your entropy. So here's S, G, and H. Entropy is in the last column. So that's 50.9, and that's a joule per Kelvin mole. And we had 2 moles of it. So this is your aluminum oxide, Al2O3, reported as 50.9 joules per Kelvin mole, and there's 2 moles of it. Minus, we have 4 moles of aluminum, which is assigned a 28.3 value, plus we have 3 gaseous moles of oxygen, which is assigned 205.2. So again, just to emphasize, this is the aluminum and this is the oxygen. Let's solve for the delta S of the reaction or the system, same thing, by taking the sum of the products minus reactants. And let's see what we get. Parentheses, 2 times 50.9, close parenthesis, minus 4 times 28.3 in a parenthesis, plus 3 times 205.2, close the parentheses, sum that, and we find a grand total. Whoops. I'm going to hit it twice just to be sure. What did you find? 2 times 50.9, we get 101.8. 4 times 28.3 is 113.2. 3 times 205.2 is 615.6. I just want to be sure we're getting an agreed answer. Alrighty, so 101.8 minus, in a parenthesis, I'll do 113.2 plus 615.6, and I got 830.6. See, I got two different answers. Which one did you get? I better hit a third time just to make sure I'm hitting this right. I always ask for a calculator buddy, and I say that sincerely because when I'm trying to talk, write, and hit the calculator keys and run the recorder, sometimes things give up. So let me just see if I can hit it once more. 2 times 101.8 is 203.6. Oh. 101.8 minus 4 times 28.3 plus 3 times 205.2 negative 627. I got this. This is it. Plus the positive didn't make sense. We said it was going to be negative. Negative 627. And I'm just going to say thank you for your patience. I like to hit that and make sure I did it correctly. And I got that answer twice, negative 627. I'm sure you did as well. All right, so that's this answer, negative 627. And if you're like me and calculators, just make sure that you're double checking calculator sequencing. It never hurts to hit things twice, especially on test day. Even the best of us make calculator mistakes, as I just showed you. So happens to all of us. Now let's try for the second part where it says the delta S of the surroundings. Now, this is the application of the third law of thermodynamics, right? We just wrote this. The entropy of the surroundings is taking negative delta H of the reaction divided by the Kelvin temperature. So a couple of things. Remember, I emphasized this must be in joules. But delta H is always given to us in kilojoules, isn't it? And so just make sure that we want our answer to come out in joules. Put in the delta H in joules as well. Let me bring our work down here for part B. The delta H was given to us right here, negative 3351.4 kilojoules. That was the given value for delta H of the reaction. All right. So what does that look like when we actually use it in our formula? Delta S of the surroundings will be calculated by taking negative of negative 3351.4 kJs per mole. And remember, there are 1,000 joules in every 1 kilojoule. So we have to move our number to make it 3 zeros bigger, right? Times 1,000. We'll put that over the Kelvin temperature. And the Kelvin temperature was given to us at standard value right here, 298 Kelvin. So that's going to go here. And that's exactly the unit that we want to end up with, is a joule per Kelvin. That's the units on entropy. So we need to take 3351.4, multiply it by 1,000. And so you could just do that in your head, I'm sure. The opposite of the negative sign makes that positive 3351,400 joules over the 298 and we get a value of 11246.3 joules per Kelvin. That number is significantly larger because the kJs had to go to joules for the enthalpy value. And this was a very exothermic reaction, wasn't it? This is a very large exothermic value. So exothermic, with that negative sign, heat is being released. And it also makes me emphasize that when we introduced entropy and determining if the reaction was spontaneous, I made a statement that said enthalpy is far more important in determining if a reaction is spontaneous as compared to entropy. And we can see that in terms of the small values here of entropy and the large values of enthalpy. We have one last job to do, and that's to sum the two values to find the entropy of the universe. So while that last answer is still on my calculator screen, I'm going to add a negative 627, and the universe then becomes 10619.3 joules per Kelvin. Summing really means subtracting here because the system was negative. That's some good work. We used the system, products minus reactants. Then we found the surroundings by taking enthalpy over Kelvin, and then added the two to find the system plus surroundings, giving us the universe. Let's ask you to try one on your own here. Pause your video and work through the following example. It's modeled just like the one we went through together. Try one on your own, come back when ready to check. Okay, welcome back. You've paused the video, tried to solve it, and let's give ourselves some feedback. Carbon in the graphite form is assigned an entropy value of 5.7. Chlorine in the natural elemental state, 223.1. And carbon tetrachloride in the liquid phase, 214.4. So the entropy of the system is going to be taking the sum of the products minus reactants. 214.4 joules per Kelvin mole minus 5.7 joules per Kelvin mole plus 2 times 223.1. The entropy of the system is found by taking the sum of the products minus reactants. Let me hit that with you. 214.4 minus, parentheses, 5.7 plus 2 times 223.1. This came out to be negative 237.5. Does that sign make sense to you? Here we have a liquid mole of carbon tetrachloride, 1 mole. Here we had a total of 3 moles, 2 of which were gaseous. Of course, that is becoming a more ordered system. 3 moles combining to just 1 mole. One of the initial reactants was a gas. So that, of course, is a more ordered system, making entropy negative. That value makes sense. Okay, now for the surroundings. We take the opposite sign of the negative 139, and I'm going to make that into joules right away, divided by the Kelvin temperature. That's fine. We're just taking joules per Kelvin. That's what the unit is we're trying to find. So I just simply am going to take 139,000 divided by 298, And we get a value here of 466.4 joules per Kelvin. The universe will be found by taking the system and adding it to the surroundings to find the universe. So it's the sum of system plus surroundings. And that came out to be 228.9. Notice here, the second law of thermodynamics would say, if that's a positive value, so I'm going to say it's greater than 0, right? If the delta S of the universe is greater than 0, then our reaction in the forward direction is indeed spontaneous. And that's exactly what happened here, isn't it? The delta S of the universe is indeed a positive number. So this reaction is spontaneous in the forward direction. Just to remind ourselves, if delta S of the universe came out negative, it's non-spontaneous in that direction. If delta S of the universe came out greater than 0, as in this example, it is spontaneous in the forward direction. And if delta S of the universe came out exactly 0, then we know that this reaction is at equilibrium. I'm going to model a couple more problems in our practice here, giving you some practice with homework. Here it says, here's a data table, and we're being asked to calculate the entropy of fusion and the entropy of vaporization for the element lithium. So that's the first line in the data table. Some people might get sodium, potassium, rubidium, cesium, just as the homework generates randomized questions. The difference here would simply be given what element you're going to focus on. Now really, I just want to just think about the units. To solve for the delta S of fusion, we want to end up with a joule per Kelvin mole, the units for entropy. The heat of fusion right now is 2.99, and that's given to us in kilojoules per mole. The temperature of the heat of fusion is 454 Kelvin. The reason I'm writing this out is all we need to do now is switch this and we get a joule per Kelvin mole. So all I'm doing up here is switching this now into a joule unit. And if I divide that by 454 Kelvin, I get the desired unit of a joule per Kelvin mole. That's all there is to this problem, is taking the units that are given and working them to what you want, a joule per Kelvin mole. Clearly you see 2.99 times 1,000 is 2990. That's our joules of heat divided by the Kelvin temperature of 454. And we get a heat of fusion that's equal to 6.17, I'll just round there, I'll put 18 joule per Kelvin mole for the entropy of fusion. That makes sense? We're going to take the heat of vaporization, but as a joule, 134,700 joules. That's sliding your decimal 3 spots to go from a kJ to a joule. We'll divide that by the temperature in the Kelvin unit, and we get the desired unit of a joule per Kelvin mole for the heat of vaporization for lithium. 134,700 divided by the temperature, 1615. And this becomes 83.4 joule per Kelvin mole. So I selected this problem to show as an example, just to let us really think about units and let that decide your problem-solving strategy. The data table gave us kJ per mole, and it gave us a temperature. We're just being asked to turn those data points into the unit of joules per Kelvin mole. So that's how we know to introduce the temperature unit on the bottom. I'd like to think through this with you as well. It's a good thought question. We're going to classify each of the phases by the signs of the system's enthalpy, as well as entropy. So let's think about that. This is a graph that we showed earlier. Here's entropy, and let's put temperature here. As the temperature begins to rise, we'll call this the solid phase. Entropy will be increasing with kinetic energy. Then the solid will actually melt. The liquid that's formed will increase its entropy as the temperature rises, and then it will actually vaporize. And then the gaseous form will continue to increase entropy as the temperature increases. So this direction is an endothermic process, and this direction, reading it the opposite way, is an exothermic process. It takes energy for a solid to melt into a liquid phase, right? That takes energy. So let's find where a solid converts to a liquid. A solid converts to a liquid. A liquid can convert to a gas, and a solid could go directly to a gas. We call that sublimation. Solid to gas, solid to liquid, liquid to gas, all require energy, endothermic. And you know what's happened along the way? This has become more disorganized, right? A dispersal of energy. That those two go together. As kinetic energy is increasing, molecular motion begins to increase as well. The system has more microstates, therefore more chaotic, an increase in entropy. How about the opposite? In the exothermic phase, when the system becomes more organized, you would have a gas go back to a liquid. That's exothermic, releasing heat and becoming more organized. You could have a liquid turning to a solid, releasing heat and becoming more organized. And you could have deposition, which is a gas going directly to a solid. Gas to solid, gas to liquid, liquid to solid. Those are all examples of phase changes that give us endothermic with a positive entropy and exothermic with a negative entropy. Good thinking problem. So as you thought about that, we place those in this direction, that in phase changes, there are no examples of endothermic becoming more chaotic or exothermic becoming more organized, right? So there's a good example of just thinking through phase changes at the molecular level. We're going to stop our lesson here. There's one more lesson we'll come back to complete our thermodynamics chapter. We'll introduce Gibbs free energy. Take a break, come back when ready.